For this video, I'm going to be discussing the concept of blackbody radiation. So firstly, please check out that video that I posted on Blackboard. It goes into the concepts of why these certain colors show up when they do with increasing energy, increasing temperature and everything. It is kind of a little bit more in depth than I expect you to know, but extra information can never really hurt you too bad. But as far as what I'm going to be talking about is the concept of blackbody radiation, how it kind of ties Planck into all this stuff here. And so first off, why does it have to be a black body? And so all I mean by black body is some object that is black. And the reason for that is because color black does not reflect any energy or light. And so you're more familiar with this concept than you ever wanted to be. If you've ever worn a black t-shirt in Texas in the middle of summer, you know wearing black is going to be a horrible idea because black color t-shirts absorb all that energy and all that heat and makes you really, really nice and toasty. Whereas if you wear a white t-shirt, white will tend to reflect more heat and more energy, and it won't make you like cook to death inside of your own clothes. And so that's the whole reason why we refer to this as black body. And so the other aspect of this is if you were to heat up a black object, it will start changing color. And so please note, I did not say I did anything else to this black body except heat it up to a higher temperature. And so when you kind of start heating these black bodies up to around 1000 Kelvin, they'll start releasing or producing this kind of like dull orangish red color. And so the good example of this is if you've ever cooked any like steak or any food using a charcoal grill, as soon as you set those coals on fire and let them sit there for a while, after some time passes, those coals will start glowing a dark orangish red color. And so this typically happens whenever you heat a black object up to about 1000 Kelvin. If you continue to heat this substance up to around 1500 Kelvin, then that dull orangish red color becomes more of a bright orangish yellow color. And again, a good example for this is if you have an electric stove, as soon as you turn that unit on, those coils heat up pretty quickly to about 1500 Kelvin, and you start seeing them change color. They're no longer black, and again, as soon as you see that bright orange color, you know you should not stick your hand on top of the stove. If you heat that black body up just a little bit more to about 2000 Kelvin, then this black body now starts glowing a bright white color. And so these are a little bit more associated with the concept of like light bulb filaments. And so as soon as you turn on that light, you're supplying energy to that black body object or that black filament, and it starts glowing a bright white color. And so this all kind of brought up a few questions when it was first kind of determined. And so one thing is how are all these things interrelated? How is like heat associated to color? And so as far as we know from all the previous information that you've hopefully read in your slides, we know that color is going to be related to frequency and wavelength. We know this because, again, every single thing on that electromagnetic spectrum, all those colors that we see in the visible light, they have a certain wavelength and a certain frequency associated with them. And so that dull orangish red color, that bright orange color, and that bright white color, they all have certain energies associated with them that refer to these wavelengths and these frequencies. And so therefore, we know somehow your heat, which is a form of energy, has to be related to your frequency and your lambda. And so the question was boggling everybody's minds at the time. And luckily, Planck is the guy who kind of like stood up and figured all this out. And so in a literal act of desperation, Planck had written so many equations and all of them were failures, he was just about to give up. But as soon as he kind of determined one last concept here, he called it Planck's constant, and he was able to tie the whole idea of energy and wavelength and frequency and color and everything else into a neat little bow. And so this final equation here, that delta E equals your H nu equals Hc over lambda, that H is Planck's constant. And so when we kind of go through and start talking about this, Planck's constant is going to be used in all of these equations in order to tie the whole relationship of delta E and frequency and delta E and lambda and everything else that's kind of associated with this. And so Planck's constant is 6.626 times 10 to the negative 34 joule seconds. And so in the future videos, I'm actually going to use Planck's constant and kind of illustrate how this stuff can be, again, determine frequency, wavelength, energy, color. Just remember, they're all interrelated.